Hey, Honors Chemistry, it's Thursday, April 9th. What I have here is chapter 17, page 528. What's the title? Reaction kinetics? Correct. By the way, I'm dressed the way I am today because it is character day and I'm dressed as a Samaritan's Purse volunteer. Of course, you know, my wife and I went down to North Carolina last summer and helped them rebuild a house after Hurricane Florence just ravaged the whole area down there. So I'd recommend that to you if you are so inclined. Now I'm on page 528, reaction kinetics. That means how fast does a reaction go? So I'm going to give you a couple speedy ones, and then I'll show you a slow reaction. So I have a little bit of zinc, metal. I'm going to stick it in here, in this little test tube. And you guys have already done this lab. So welcome back to something that you know. Not putting in too much, just to get it started. I'll stick it right here, and I'll cover it up with a collection test tube, and we'll collect that oxygen. That hydrogen, and then we will pop it. So we're going to put zinc together with hydrochloric acid. Once again, be careful. So I'm not going to wear my glasses. I've got my glasses on. Talking about the other ones. Okay, here we go. Watch this. Will it happen fast? I guess so. Pretty fast. So we'll cover it up, gather up some of that hydrogen. And while that's going in there, we'll make ready our wood burning splint. Okay. Got this. Got this bad boy so I don't burn my fingers. Okay. And then we'll see if we got any oxygen in there, hydrogen in there already. I guess we do. Okay. So there you go. Let's take a look at that on the board. First equation went like this. We're going to take solid zinc, combine it with hydrochloric acid. We're going to call that aqueous. And we're going to get zinc chloride, solid, and we're going to get hydrogen gas released. Sometimes instead of gas, they'll put an arrow going upward, you know that. So what's happening here? Well, this right here is hydrogen ions swimming around in chloride ions, in water, I mean. And those bad boys, that's easy grabs, because this thing wants to lose electrons. Got it? And that's called oxidation. And this thing wants to gain electrons, it's going to become reduced. That's chapter 19, you don't need to know that. But because it's so easy pickings, it's going to happen rapidly. The hydrogen's going to come off rapidly. Then after we got the hydrogen, we popped it. And so now we have hydrogen gas and the oxygen gas in the room producing H2O gas. Water vapor, but as soon as we produce the water vapor, of course, you can see that there's film on the inside of this thing where it condensed as soon as we popped it. So it condensed into liquid. But these things combine rather rapidly in the presence of heat. Put a triangle above the arrow. That means in the presence of heat, that thing will drive in that direction. Okay, so what is on the outside of a hydrogen molecule? Well, not much, because hydrogen molecules look like this. Boom. But what's on the outside of oxygen molecules? Well, you got a bond here, a double bond, and then you've got lone pairs. And so you take that molecule and you go together with this molecule, and these electrons here, they're not just between the atoms. I mean, they're kind of moving around, right? Those electrons interfere with those electrons. And so what happens with molecules is the electron repulsion prevents them from getting close to one another to make a reaction. So sometimes that slows things down. But you see here, in the presence of heat, there's enough energy to drive them together against the bonds of repulsion and overcome them. Now, this is a slow reaction. And the reason that this galvanized nail, galvanized just means that the steel is coated with zinc in order to prevent some of the oxidation or the corrosion. And you can see that right up here, we've got some rust. Iron oxide, iron 3 oxide, Fe2O3. And that's slow because that nail did not rust overnight. It didn't rust even over weeks. It rusted over a long period of time. When you take iron and expose it to air, it's going to rust. If you want it to rust faster, you're going to expose it to water. And of course, there's water vapor in the air, and there's water in the ocean, and there's a sunken wreck in the ocean. It gets real rusty because the water acts like a catalyst. A catalyst is something that speeds up a reaction without itself becoming part of the reaction. And then the salt is also a catalyst, and so it speeds up the reaction as well. So this nail, if you threw it into the deep blue sea, would probably rust a whole lot faster. However, it's still pretty slow compared to what we just saw. And so the reaction process is something that we want to study to find out the kinetics of reaction. In other words, how fast does it happen? And in this little section, section 1, we're going to only discuss molecular interaction. We're not going to take, well, for example, let's suppose you dissolve salt. I think I've done enough. When you've got ions together, well, let's just say it real quick, okay? We're going to take some hydrochloric acid, we're going to combine it with sodium hydroxide, and we're going to get sodium chloride, that's the salt, and we're going to get water, that's the water. And that's acid-base neutralization. You already know how to do this. But what is it that's really happening? This is in water. So you got hydrogen ions, and you got chloride ions, and you've got sodium ions because they're in water, and you've got hydroxide ions. And whenever you've got that thing going on, this is heavily attracted to that right there, and then just opposites, boom, it's electrical attraction. It happens rapidly, and this forms the water molecule, and that happens rapidly as well. So when you're doing acid-base neutralization, it happens in the flip of a switch. All right, so now almost instantaneously. We're going to go ahead and talk about this equation you see on the bottom of 529. We're talking about hydrogen gas combining with iodine gas to form hydrogen iodide. So we got hydrogen gas combining with iodine gas, iodine vapor we call it, and forming hydrogen iodide gas. Now, this first one is clear. You saw the hydrogen forming, and you didn't see the hydrogen because it was clear. The iodine, if you remember, when I did my sublimation example, we had these little flakes of iodine. I put them in a beaker, put them on a hot plate, and it formed all of this purple colored gas. Call it violet or lavender. I don't know if that's ER or what. Okay. And then it forms a clear. But after this forms, it tends to break down back into its constituent gases. But they reform into that molecule, those two molecules, but then they break down into their constituent gases. So what I do to demonstrate this is I create some hydrogen gas, similar to what I've done here. Underneath, there's a hot plate, and I get it up to elevated temperatures, and that causes this to sublime into a vapor. And then I have some hydrogen gas that I make because of zinc and hydrochloric acid, and then I pump it into this little, combine them in a flask. There you go, Erlenmeyer flask. And when I combine them, they're going to look lavender. Just for a while. But then after a little while, it's going to turn lower lavender, more of a pink. And then after it turns pink, it's going to turn clear. But then after it turns clear, it's going to come back to pink again. And it's oscillating. And why is it doing that? The reason it's doing that is because it's a reversible reaction. And so initially it's lavender because this is what you've got. But then the more and more of this that it makes, then they mix together, it turns that lavender back down to a pink. But the more of that it makes, then it breaks down and it returns to this side over here, lavender, but there's still some clear over there mixing in there. So it's somewhat of a light pink after that. And this is called equilibrium, but it has to take a little time for it to establish equilibrium. So the question is, what's the reaction mechanism that gets it to that stage of reaction? And so what is a reaction mechanism? On page 529, it's the step-by-step sequence of reactions by which the overall chemical change occurs. Now let's flip the page. There are these things called intermediates. What is that? Well, intermediates are species that appear in some steps, but not in the net equation. They're known as intermediates. So here's the reaction that we're dealing with right here. So let me erase some of this. And the question is, how does it get from here to there? Do these molecules combine to form that? Well, they found out that there is not a direct reaction between hydrogen and iodine. It just doesn't take place. Something happens in between. There are two suggested reaction mechanisms, two potential reaction mechanisms. The first one on page 530 in the middle suggests that it might be two steps. And then the second possibility is that it's a three-step. So what happens here? Well, what happens first is that the iodine, oh, I forgot to put the two there. The iodine breaks down into two iodine atoms. And in those two iodine atoms, combined with, let me do it over here, this hydrogen here. So the hydrogen wasn't in the game until the iodine broke down. And when it combines with hydrogen gas, it forms that. So what is the intermediate? The intermediate in this particular case are these. So what do you have left when you eliminate the intermediates? You have that equation right there. Now, is that really the way it happens? It's a theory. The theories, you don't know for sure if that is exactly, it's just a probable sequence that they think may be happening. There's another potential. It's the next reaction mechanism. The iodine breaks down into two. By the way, these are reversible reactions. And then one of those two, just one of them, reacts with the hydrogen gas. And that forms hydrogen iodide. They say H2I. And then the H2I combines with the other iodine. One of them is used here, and the other one is used here. And so it forms H2, two HI molecules. So there are three steps in this reaction mechanism instead of two. And this is just, again, a theory, a proposed theory. And so what is it that is eliminated that are intermediates? Well, are these right here. There's two over there, there's two over here. And it's these. So in these cases, there are two different types of intermediates. And what do you have left? You have the target equation. Now, I want to talk to you about these things here. You know, iodine is a diatomic element. What does that mean? It means the atoms do not exist by themselves. They only exist in pairs. They cannot come over here like this. This would be called iodine nascendi. I think that's the word. And I think the nascendi is like a Latin word that means it's giving birth. In other words, it isn't there yet. And so iodine really wants to have a buddy. And so it's looking for electrons anywhere it can get them so that it can clump up. If it doesn't get them from another element like hydrogen, it'll buddy up with each other. And so it happens that it reacts explosively and quickly because these nascendi atoms, and that would be which elements? Well, you got hydrogen that works that way. It's never by itself. And then you got the ones down the halogen series, group 17. And oh, I could look right here on my periodic table, of course. The others are fluorine, chlorine, bromine, and iodine. There you go. Diatomic elements. So what's collision theory on page 530? Collision theory says this. The set of assumptions regarding collisions and reactions is known as collision theory, and they talk about it all the time in experimental science. So you'll hear that word used often. The question is, will there be a reaction? Look on 531 at that figure 1.3. Figure 1.3, the top picture, picture A. That's an effective collision. The reason is because you need two things. You need enough energy to react, and you also need proper orientation of the molecules. If you look at the top picture on 531, you see a blue atom and a little gold atom underneath it there. And so that's a compound AB. Those aren't really atoms. They're just a figure that is showing you a compound. Compound AB smacks into compound AB, and they bounce off, and then diatomic element A, A2, pops out the bottom, and then atoms B push out on the sides. That's effective collision. So it has enough energy when they smack to blow it apart and reorient the atoms. It's kind of like burning a log. And it falls to pieces. The log falls to pieces into its constituent elements, you might say. And then picture B. That collision was too gentle. It didn't have enough energy. And so therefore, it just hit one another, boom, and then bounced off, boom. And the molecules AB go on their merry way as though nothing ever happened. Why do they have to have enough energy? Well, they got to overcome the resistance of the electron clouds. And then picture C, the collision doesn't have the proper orientation. Do you see, in order for the gold atoms to squirt out the bottom, they got to be together in the middle? If you look at the orientation on picture A, you see that they're together in the middle. So when they collide in picture C, they're protected by atom B, the blue atoms. And so they don't squirt out the bottom, the blue atom, the compounds go on their merry way. So the example on the bottom of 531 is, if you're going to combine nitrogen monoxide with chlorine gas, the chlorine has to hit the oxygen side of the molecule. Otherwise, the orientation is not favorable for their reaction to take place. If the chlorine gas hits the nitrogen end of the molecule, they will not stick. Now I'm going to start on 532 on this next lesson. See ya.